Detecting environmental toxins with microfluidic platforms is transforming how we monitor nature's health, offering rapid, on-site analysis of hazardous chemicals that could threaten ecosystems and human well-being. Imagine a device no larger than a smartphone, capable of analyzing water, soil, or air samples in minutes rather than days. These platforms leverage tiny channels and chambers etched into a chip to carry out complex chemical assays. Everything from detecting lead in drinking water to spotting pesticide residues in agricultural runoff, all with extraordinary sensitivity. One of the most unexpected facts is the sheer sensitivity of these devices. They can detect toxins at parts per billion levels, meaning even the slightest contamination doesn't go unnoticed. For example, some microfluidic sensors have been engineered to identify mercury, a heavy metal notorious for its damaging effects on wildlife and humans, long before it reaches harmful concentrations. Isn't it fascinating that such a minuscule chip can serve as an early warning system, potentially preventing a major environmental disaster? Consider a river running through an industrial area. Traditionally, samples would need to be taken and sent to a distant lab, delaying crucial decisions. With microfluidic platforms, sensors can be deployed along the river to continuously monitor toxin levels in real time. When a sudden spike in pollutants is detected, local authorities can quickly investigate and mitigate the issue. This leads to an intriguing question: could these devices one day enable a network of smart environments that automatically report pollution incidents to protect both nature and communities? Current research suggests that this is not only possible, but increasingly practical, with advances in miniaturization and sensor technology. Another compelling example comes from the realm of air quality monitoring. Microfluidic devices can capture airborne toxins like volatile organic compounds, VOCs, released by industrial processes by directing a small air sample through microchannels lined with reactive materials. These materials interact with the toxins, producing a measurable signal that indicates both the presence and concentration of the hazardous chemicals. This kind of real-time monitoring is crucial in urban areas where air pollution can change rapidly and have significant health impacts. Moreover, these platforms aren't just limited to chemical detection. They can be integrated with digital data systems to provide immediate feedback and even predictive analytics. Imagine a scenario where a microfluidic sensor detects an unusual chemical signature in a water source. It could instantly relay data to a central system that uses machine learning to forecast potential environmental or health impacts. A proactive approach could revolutionize how we manage environmental risks, shifting from reactive measures to prevention. In summary, microfluidic platforms for detecting environmental toxins offer a groundbreaking fusion of chemistry, engineering, and data science. They empower us with rapid, accurate, and on-site analysis that could redefine environmental protection. As these technologies continue to evolve, they raise exciting questions. How soon will we see widespread deployment of smart environmental sensors? And how will real-time toxin monitoring reshape our efforts to preserve the natural world? With every innovation, we move closer to a future where our ability to safeguard the environment is as dynamic and responsive as nature itself. Microfluidic platforms have emerged as powerful tools for detecting environmental toxins quickly and accurately. They are engineered to handle extremely small volumes of fluid, which is ideal for analyzing trace amounts of hazardous chemicals. These devices integrate multiple laboratory functions on a single chip, streamlining the detection process. They can analyze samples from water, air, or soil, making them versatile for environmental monitoring. Their compact size and portability allow for on-site testing in diverse natural settings. The rapid analysis provided by these platforms is crucial for timely decision-making during environmental emergencies. They reduce the need for centralized laboratories, enabling real-time detection in the field. This technology represents a significant advancement in environmental safety and public health protection. A research team deploys a portable microfluidic device at a river site to test water samples for the presence of industrial pollutants, delivering results within minutes. Imagine having a handheld device that works like a mini laboratory in your pocket, instantly checking the quality of water, just as a home water filter tests and signals if something is wrong. Microfluidic principles rely on the precise manipulation of fluids through microscale channels and chambers. These principles allow for controlled reactions and interactions between sample fluids and detection reagents. The technology exploits phenomena such as laminar flow and capillary action to maintain stable and predictable fluid behavior. This precise control is essential for reliably detecting minute concentrations of toxin. It also minimizes the use of reagents, making the process both cost-effective and environmentally friendly. The small dimensions of the channels lead to rapid diffusion and efficient mixing of reactants. These characteristics enable quick reaction times, which are critical for real-time environmental monitoring. Overall, microfluidic principles create a robust platform for sensitive and rapid toxin detection. Engineers design a microfluidic chip that channels a water sample through a series of reaction chambers, where it mixes with specific dyes that change color in the presence of heavy metals. It is like a tiny, well-organized assembly line, where every drop of liquid is carefully directed and mixed to reveal hidden impurities, much like a precise machine sorting and analyzing ingredients for a perfect recipe. The design and fabrication of microfluidic sensors involve advanced techniques such as soft lithography, 3D printing, and photolithography. These methods enable the creation of intricate channel networks that can detect specific hazardous chemicals. Materials used in fabrication are carefully selected to ensure chemical compatibility and durability in harsh environmental conditions. The sensors are designed to be highly sensitive, capturing even low levels of toxin. Their miniaturized format allows for rapid response times and high-throughput analysis. The fabrication process also focuses on creating robust devices that can be easily deployed in the field. This meticulous design and fabrication ensure that the sensors perform reliably under variable environmental conditions. A team fabricates a microfluidic sensor using soft lithography to create a network of channels on a polymer substrate that is then functionalized to detect pesticide residues in agricultural runoff. It is like crafting a detailed, miniature maze where each pathway is carefully engineered to guide and detect specific signals, similar to building a custom-designed security system for a building. Integration of detection reagents and sensors is a critical step in microfluidic toxin detection platforms. Specific reagents are introduced into the microchannels to react with targeted hazardous chemicals. These reagents often include colorimetric or fluorescent markers that signal the presence of toxins. The sensors capture these signals and convert them into quantitative data. This integration ensures that the detection process is both sensitive and selective. It also allows for real-time monitoring and immediate feedback. The system is calibrated to differentiate between various toxins based on the unique responses elicited by each reagent. Ultimately, this integrated approach enhances the overall reliability and accuracy of environmental toxin detection. A microfluidic device is designed with integrated fluorescent sensors that detect changes in light intensity when water samples react with specific chemical markers for industrial solvents. Imagine a high-tech paint that changes color when it comes into contact with certain substances, with built-in sensors that immediately alert you to the change, much like a smart indicator light on a car dashboard. Rapid sample processing is one of the major advantages of microfluidic platforms in toxin detection. These devices can handle and analyze tiny sample volumes swiftly, leading to immediate results. The miniaturized channels and reaction chambers accelerate chemical reactions and mixing. This speed is crucial for on-site environmental monitoring where time is of the essence. Automated sample processing minimizes human error and ensures consistency across multiple tests. The rapid analysis enables quick decision-making during environmental hazards. It also supports high-throughput screening, allowing many samples to be processed simultaneously. Overall, rapid sample processing is fundamental to effective and timely toxin detection in nature. During a suspected chemical spill, first responders use a microfluidic device that processes water samples in less than 10 minutes, determining the level of contamination rapidly. It is like using a high-speed blender that not only mixes ingredients instantly, but also provides you with an immediate taste test, ensuring you know exactly what's in your smoothie without delay. Sensitivity and specificity are crucial performance metrics for microfluidic toxin detection systems. Sensitivity ensures that even very low concentrations of hazardous chemicals are detected accurately, while specificity ensures that the device can differentiate between various types of toxins without interference. The design of microfluidic platforms allows for fine-tuning of these parameters through optimized channel geometry and reagent selection. Advanced sensor integration further improves the system's ability to provide precise readings. This results in high confidence in the detection results, even in complex environmental samples. The combination of high sensitivity and specificity is essential for reliable environmental monitoring. Ultimately, these attributes enable effective identification and quantification of toxins, ensuring environmental safety. A microfluidic sensor demonstrates high sensitivity by detecting parts per billion levels of mercury in water, while also distinguishing it from other metals like lead and cadmium. It is like having a super sensitive smoke detector that not only picks up even the smallest traces of smoke, but can also tell whether it's coming from a candle or a fire, ensuring you get the right alert. Data acquisition in microfluidic toxin detection involves collecting real-time signals from the integrated sensors. These signals are converted into digital data that reflect the concentration and type of toxins present in the sample. Advanced software and algorithms process the data to generate clear, actionable results. The system can analyze data in real time, providing immediate feedback to the user. This rapid data interpretation is essential for making timely decisions in environmental monitoring. The digital output is often displayed in an easy-to-read format such as numerical values or color-coded indicators. The accuracy of data acquisition directly impacts the reliability of the toxin detection process. Ultimately, efficient data acquisition and interpretation enable effective monitoring and response to environmental hazards. A field-deployed microfluidic device transmits data via a wireless connection to a central monitoring station where software algorithms interpret the signals to provide a real-time map of toxin concentrations in a lake. It is like a smart thermostat that not only reads your home's temperature instantly but also processes that information to adjust the heating or cooling system in real time, ensuring optimal comfort. Deploying microfluidic toxin detection platforms in the field presents several challenges that must be addressed. Environmental factors such as temperature fluctuations, humidity, and contaminants can affect device performance. Robust device design and protective housings are essential to ensure reliable operation in harsh outdoor conditions. Calibration protocols must be established to maintain accuracy across diverse settings. Additionally, ease of use is critical for non-specialist operators in remote areas. Strategies such as ruggedization and portable power solutions are implemented to enhance field performance. Ongoing research is focused on developing devices that are both durable and user-friendly. Addressing these challenges is vital for the successful deployment and widespread adoption of microfluidic toxin detectors in environmental monitoring. Engineers are developing a ruggedized microfluidic sensor with waterproof and dust-proof features that can operate reliably in extreme weather conditions while detecting air pollutants in urban areas. It is like designing a durable smartphone that can withstand drops, rain, and extreme temperatures, ensuring it functions reliably no matter where you take it. The future of microfluidic platforms for toxin detection is bright, with ongoing advancements set to enhance their capabilities even further. Researchers are exploring new materials and fabrication techniques to improve sensitivity, durability, and ease of use. Integration with wireless networks and cloud-based data analytics will enable real-time environmental monitoring on a global scale. These advancements will allow for the rapid detection of emerging contaminants and early warning of environmental hazards. The technology is expected to become more affordable, facilitating widespread adoption by governments and communities. Enhanced data interpretation and automation will make toxin detection more accessible to non-specialists. Ultimately, these innovations will contribute significantly to environmental safety and public health. Future developments may include a network of interconnected microfluidic sensors deployed in water bodies worldwide, continuously monitoring for industrial toxins, and sending real-time alerts to environmental agencies. Imagine a smart, interconnected network of weather stations that not only predicts storms, but also monitors air and water quality, ensuring that every community is protected from potential hazards before they become disasters.